Okay, so I want to quickly talk about what we did last time. So we did this last time. You don't need to look for this page. What I want to talk about is what we did last time is we have two different sets of data, but the data have a relationship. They are paired in some way. Our two different samples are dependent. So in this case, we said both of the young women were going to the store at the same time. So they were not independent, which was called a matched pairs procedure. And the big thing with matched pairs is that all we cared about were the differences. So we didn't actually care about those two data sets. All we cared about was when we subtracted them. All that sound familiar? What we're going to take a look at today is, again, we have two data sets, but they are independent. There's no relationship between them. So I need you to find this page, 10.2. So we're going to be looking at mean again. We are going to start with sampling distributions. So if we look at the sampling distribution of just plain old X bar, what do we know about it? First thing, shape. We know that the shape is approximately normal if n is greater than 30, so if the central limit theorem applies, or the population is normal. The center. We know that the center of our sampling distribution is equal to the population parameter. And if you remember, that is because X bar is an unbiased estimate of mu. It does not mean that if we take a single sample that X bar will be equal to mu. It means in the long run, if we were to take all the possible samples, we're not going to systematically over or underestimate. And then the spread. The spread of our sampling distribution is equal to the standard deviation of the population over root n. This is the formula, though, that requires our sample size to be less than the population. So all of that we've talked about. What we are looking at today is we have two samples, and so we will have two different sample means. And we will be looking at subtracting those two sample means. So we'll have sample 1, calculate that mean. Sample 2, calculate that mean, and then subtract them. And we want to know what is true about the shape, center, and spread. It's going to be pretty similar. The shape is going to be approximately normal if this time, for the central limit theorem to apply, both the sample sizes would have to be bigger than 30, or both populations would have to be normal. The center is fairly intuitive. The center of x1 bar subtract x2 bar is the center of the first subtract the center of the second. This is the one that is not intuitive. So what a lot of people want to do for standard deviation is they want to say the standard deviation of x1 bar subtract x2 bar. Well, I just do the standard deviation of the first population, and I subtract the standard deviation of the second population. And that is not true. That is not true. There's two issues. Any ideas what might be wrong? Oliver?
Different sample sizes.
Okay, yeah. Sample sizes are different. That's true. If we think back to transformations, so let's go down here to where these formulas come from. If you remember back to something like this, and if we said the standard deviation of standard deviation of x was 4, and the standard deviation of v was 3, if we were finding the standard deviation of z, could we just do 4 subtract 3? What did we have to do instead? There were two golden rules. Okay, had to be variance. So instead of 4 and 3, we had to square them. That was golden rule number 1. What was the other thing? My mantra was always variance, always add. Always variance, always add. Okay, so it's a similar idea here then for the sampling distribution. We're going to have to square to get variances, and we're going to have to add them. So if I'm looking for the standard deviation of x1 bar subtract x2 bar, I will have the variance of the first one add the variance of the second one. But then ultimately I'll have to take a square root to get standard deviation again. And again, our first sample size would have to be less than 10% of that population, and our second sample size would have to be less than 10% of that population. These formulas are on your formula sheet. So these formulas are on your formula sheet, but now you know where they come from. These are the ideas that we are going to use when constructing our confidence intervals and doing our hypothesis tests. Questions? Okay, so like I said, we're going to do a confidence interval together, and you will do a hypothesis test in your group. So the conditions for performing inference, again, when you see inference, that just means a confidence interval or a hypothesis test. Right now we're in the confidence interval section, but the conditions are the same for a hypothesis test. We are looking at the difference in two means. So ultimately we'll be looking at mu1 minus mu2. The conditions are pretty similar when there's just one mean. What is the first assumption always? Random. Okay, this one is going to look a smidge bit different. You need to have independent random samples, or when I say independent random samples, this would be in the case of we have an observational study. So we have an observational study and we are comparing two groups. If we have an experiment, though, and we are comparing two treatments, oftentimes in an experiment, there is no sampling. So it doesn't make sense to say that our samples are random because we didn't have samples. We probably had volunteers for our experiment. What does random mean in the case of an experiment? Randomly assigned treatments. So if it's an experiment, the treatments need to be randomized. So this, I would say, is the most common mistake, is this first assumption. A lot of times people will only check random samples. But the key here is we need to know, is it an observational study or an experiment? Second, approximately normal. We have to check that again for both sampling distributions. So both sampling distributions are approximately normal. And you still have the same three ways to check. Either you would be told a population is normal, or you're going to use the central limit theorem, or you would look at a graph. It is possible that you would check for the two samples differently. So it's possible central limit theorem would apply to one sample, but not the other one. And lastly, you would need to check the 10% rule for both samples if the three things we talked about last class, if we are sampling and it is without replacement from a finite population. So what I'm trying to say there is if it's an experiment, you don't need to check the 10% rule. If it's an experiment, in all likelihood, there was no sampling done. Like we said, most of the time you just have volunteers. So if it's an experiment, you often do not check the 10% rule. But the big thing here that I need us to see is that you are checking these assumptions for both samples. So it's kind of like doing double work a little bit. Has to be checked for both samples. Okay, standard error. Oftentimes we don't know the standard deviation of the populations. So our standard deviation of the sampling distribution, we said is the first variance add the second variance. But we've talked about before that's not realistic. Oftentimes we don't know sigma. We don't know the standard deviations. So instead what we do is we use the sample standard deviations. This formula is on the formula sheet. And this is the typical deviation of, if we have our two samples and we subtracted their standard deviations, and we did that a whole bunch of times. So we took two samples a whole bunch of times and we subtracted their standard deviations. It is the typical deviation from those values to our true population. We got a few more things to write down, and then we will do an example. Okay, we're still talking about confidence intervals. So what is the formula? On your formula sheet, it says statistic plus or minus critical value multiplied by the standard deviation of the statistic. And again, we are looking at the difference in population means. So mu is the parameter. If I want the statistic that goes along with mu, that's just x bar. So my statistic is x1 bar subtract x2 bar plus or minus. Critical value is just t or z. So we've talked about for mean, you're going to use t. And then the standard deviation or the standard error, we often don't have sigma, so we're going to use s. So that is that s1 squared over n1, s2 squared over n2. We'll talk about degrees of freedom. We'll talk about t. I'll show you the calculator, but that's the formula that you're going to need. As a quick reminder, when would we use z? So in place of t, that's a z. I can tell that's not very clear. So instead of using t, we would use z in what case? The very, very rare case that we know what? Population standard deviations. So that would be sigma 1 and sigma 2. Okay, so we are going to do a full confidence interval example, and then we will take a break. Sound good? Okay. Here's the example that we're doing. Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as name brand chocolate chip cookies on average. To investigate, they randomly selected 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies and randomly selected one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. Here are their results. Construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. Okay, so first thing I need us to notice here is in our mind we're thinking, okay, this is mean. And I have two means, or I have two samples. So in the case where we're looking at mean and we have two different samples, we need to ask ourselves, are these samples paired? So is this matched pairs, or are they independent? So if we look at the first observation, 17 and 22, is there any relationship between these two cookies? They were chosen from the same bag. Is there any relationship between them? Is there any reason to think that the 17 chocolate chips here has a relationship to those 22? No. So because of that, we know these are independent. This is not matched pairs. Okay, so this is our new procedure. So since these are independent, we need two parameters. So we will need mu1 for the first sample and mu2 for the second sample. So mu1 is going to be the true mean number of chocolate chips in Chips Ahoy cookies mu2 then will be the true mean number of chocolate chips for Great Value cookies. Okay, so we are constructing a two-sample, 99% confidence interval for, some people say mean, some people say difference in means. So two-sample, 99% confidence interval for two means using T with, we got to figure out degrees of freedom. So degrees of freedom has typically been n minus 1. So if we look at our two sample sizes, we would do 10 minus 1 for the first sample, and we would do 10 minus 1 for the second sample. Happens to be the same number. You choose the smaller value. In either case, it's 9. So you're going to choose the smaller number. Now we have to check our assumptions. So the first one is the one that I said that people tend to mess up, and that is the random part. Is this an observational study or an experiment? Observational study. This is not an experiment. We're not assigning anything to these cookies. So the cookies need to be randomly chosen, which we're told. Randomly selected 10 bags, randomly selected one cookie. They also need to be independent. Independent will never be stable. Is there reason to believe that choosing the cookies out of the Chips Ahoy bag had any effect on the Great Value cookies? They're independent then. So we are going to say the samples are independent and random, as stated. Second assumption is the approximately normal sampling distributions. That has to be checked for both samples. So, were we told that either population was normal? No. Does central limit theorem apply to either sample? No. So we're going to have to draw two different box plots. One for the first sample, one for the second sample. So what I would like you all to do right now is, on your calculator, put the Chips Ahoy in list 1, put the great value in list 2. And you should be able to take a look at both box plots at the same time. So you will use plots 1 and 2. So I went back to back, or comparative box plots. I want two box plots on top of each other. Chips Ahoy on top, and then great value. Okay, so then of course we have to write something. We're going to say both sampling distributions are approximately normal because the samples do not show extreme skewness or outliers. College Board is very picky in grading this, that this assumption is checked for both distributions, that there is pluralness happening. If it even sounds like you only checked it for one distribution, you will not get credit. Okay, and then 10% rule. We are sampling cookies, so we do, of course, need to check the 10% rule. Well, we're sampling cookies, probably without replacement. And this is a finite population. There's a finite number of cookies in the world. And so we need our first sample size to be less than 10% of that population, and we need our second sample size to be less than 10% of that population. So the first sample is the Chips Ahoy, so we need 10 to be less than 10% of N1. So our first population has to be greater than 100, and likewise our second population has to be greater than 100. And in this case, we're actually sampling cookies from bags, so we need this many bags. Again, I don't care about the inequality. If you just have an equal sign, that's fine, as long as in your sentence you tell me more than. So, yes, there are more than 100 bags of Chips Ahoy cookies and more than 100 bags of great value cookies. Okay, finally, we're ready to actually calculate the interval. So our statistic, like we wrote, is x1 bar subtract x2 bar. We're using t, and then we have our standard error. Okay, so we will need to find both sample means and both standard deviations. You have two different options on the calculator. Option 1, you can do 1 var stats for list 1. That would give you the first sample mean and the standard deviation. And then you would do 1 var stats for list 2. And that would give you the second sample mean and the second standard deviation. Or a new function on the calculator that we haven't used yet is right below 1 var stats. There's actually 2 var stats. And you would tell the calculator I'm using list 1 and list 2. And then it would give you all 4 numbers. So what I want you to do right now is pick one of those two and go find both sample means and both sample standard deviations. And you should get 18.4 and 19.4 for the sample means. Last thing we need is t. So to remind you, to find that t, we look on the table. "99% confidence, 9 degrees of freedom." So I already did that for us, and you get 3.250. Okay, so then our interval ends up being -5.1224, comma 3.1224. The fact that the decimals are the same is just a coincidence. That will not always be the case. Remember, negatives are possible because we're taking a difference. We're subtracting two numbers, so that difference can be negative or positive. Okay. We're going to write a conclusion, answer part B, and then we will take our break. So for our conclusion, we have our two sentences. We need to interpret that interval, and we need to interpret what the 99% means. So first, the interval. I am 99% confident. The interval, -5.1224 to 3.1224, contains the difference in true mean number of chocolate chips in Chips Ahoy and Great Value cookies. Alex?
Does it matter which one you put first? Like putting Chips Ahoy Beats in Great Value?
It's not going to be a huge deal. I would be consistent with how you defined your parameter. So whichever one you defined as mu1, put that one first. Our second sentence is interpreting the confidence level. So I want to make sure we recognize that. The first one is interpreting the interval. The second one is saying what the 99% means. And this is the one that goes, if we take many, many samples and construct confidence intervals for each, about 99% of the intervals will contain the difference in true mean number of chocolate chips. And I'm just going to say ... You can fill in the rest of the context. I'm going to move up to look at part B, but then I'll come back down. So we also still have to answer part B. Does your interval provide convincing evidence that there is a difference in the mean number of chocolate chips? What do you guys think? Is there convincing evidence of a difference based on our interval? If we had done a hypothesis test, do you think we would have rejected the null or failed to reject the null based on this interval? Augie? Why?
Because 0, which would mean that they're equal, falls in the interval.
Okay, thank you, yes. The whole deal here is that 0 is in the interval. So it is possible there's no difference. Okay, try to use the term convincing evidence because College Board likes that term. So no, there is not convincing evidence of a difference because 0 is in the interval. And I told you last time that is not enough. You need to tell me what 0 means. So 0 indicates it is possible that the true mean number of chocolate chips is the same for Chips Ahoy and Great Value cookies. And then one last thing before we take our break. I've seen this once on the AP test, and so I want to tell you just so that you're aware of it. Questions like this come up quite often, and if I were grading this question, I would grade what we've written in blue as perfectly acceptable and correct. I've seen before, though, that College Board specifically wants hypothesis test vocabulary, which is what I'm going to write in green. So I've seen where College Board would expect we fail to reject the null, for a given level of alpha. Here's how you figure out what alpha would be. 99% means the rate of a type 1 error is 1%, so our alpha would be 0.01. Similarly, a 95% interval would mean that our alpha was 5% or 0.05. So I've seen this at least once, if not twice, where to get full credit you would have to use the hypothesis test vocabulary. So just for you to know. Okay, so now we're going to do a hypothesis test. We're going to do a full hypothesis test. And it is this problem that is in your notes, so I will leave this up here, and I'm going to get us started. McDonald's average service time for 362 drive-through visits was 188.83 seconds with a standard deviation of 17.38. Burger King's service time for 318 drive-through visits had a mean of 201.33 seconds and a standard deviation of 18.85. Is there a significant difference in mean service time for McDonald's and Burger King? Okay, so in this case, it blatantly tells us that this is mean. We have to ask ourselves, is there any relationship between the two sets of visits? Were they done at the same time, the same town, anything like that? No. So we're telling ourselves this is not matched pairs. Not matched pairs, so these are independent. So in our choose step then, you will have to define mu1 and mu2. I'm just asking us to start with mu1 together. What would mu1 be? The true mean service time for McDonald's. Okay, so before I let you go to keep going, I want to tell us what the null and the alternative are. We are assuming there is no difference. So we are assuming that one mean is equal to the other mean. You will also see this written as mu1 subtract mu2 equals 0. Either of those are acceptable. You do not need to write both. They mean the same thing. What we want to know is there a difference? So we want to know, is there evidence that mu1 is not equal to mu2? And again, the other way to write that is mu1 subtract mu2 is not 0. You don't need to write both. They have the same meaning. So when I'm done talking, you will do this hypothesis test on your desk with your group. You can just take pictures at the end. You don't need to write this down. Just take pictures and put that in your notes. That's fine. I will be stopping us at various times to go over some things that we need help with. Good luck. Okay, so we've checked our assumptions and we're now at the point, or we're getting close to the point of calculating. If you remember, for a hypothesis test, you're going to need a test statistic, which in our case is t, and we're going to need a p-value. So really, what I need to help us find is the test statistic. Okay, on the formula sheet is going to say statistic, subtract parameter, over the standard error. Well, we already know this. We already know statistic at least. That just comes from the confidence interval formula. That is subtracting our sample means. When it says parameter, that just means what's in the null. Well, if we write the null like this, it's not particularly clear. But when we write it as a difference, we see we're assuming the difference is 0. And then the standard error, like we did in the confidence interval, is that square root. Then, once you get that t-value, you will draw your figure, you'll find your p-value, so on and so forth. So I think you are now at the point where you can finish the hypothesis test. So this is where I'm going to leave you. If you have questions, let me know. Okay, here's my answer key. It says the state plan do conclude, but it's the same idea. Things I want to point out to us. We need to say that this is a 2-sample hypothesis test for 2 means, or difference in means. The samples need to be independent and random. I get lazy, and I often write distribution as DIST period. We need to make sure we somehow indicated that there were 2 distributions. So if you want to abbreviate distribution but put the word both, that's fine. You got to have the word sampling in there, but you have to somehow show that it was checked for both samples. And then you do need to check the 10% rule. A lot of us didn't because we said, oh, it's an infinite population. We're not looking at time. We're looking at people that actually visited or actual visits to McDonald's and Burger King. There are a finite number of visits. So that does need to be checked. Please make sure you used T. A lot of times what I see is that we write T all the way up in the first step, but then we start to use Z. So T needs to be there. And we say, yes, there is a difference in the mean service times. And then we should have interpreted the p-value. My interpretation is going to be a little different probably than yours. So a lot of this is very similar to what we've been doing. Karina.
Where did the negative 12.5 come
That is such a good question. Okay, thank you for asking that. This negative 12.5 comes from the actual difference. So these are our two sample means. If you subtract those, that's the negative.